Hello, my name is Maxim Strutovskiy. I am going to present the work of our team Desbordante, a framework for exploring limits of dependency discovery algorithms. A dependency in a database is a rule or a pattern present in the table. Dependencies can be employed in many tasks, namely data exploration, schema normalization, and data cleaning. Dependency discovery is a relevant topic. In this work, we focus on functional dependencies, which are a specific dependency subtype. Let X and Y be attribute sets. X functionally determines Y if two tuples sharing the same values of X have the same values of Y. However, real data contains typos, missing values, and noise. This results in scenarios when NFD cannot be inferred, but common sense or domain knowledge implies that such an FD exists and has to be found. A special class of algorithms addresses the problem of dirty data. Approximate FD mining algorithms. An approximate FD holds if a fraction of broken rows, which agree on X but disagree on Y, is less than a specified maximum value. FDs embody business rules. If an expert cannot identify these rules, one can use the automatic discovery of dependencies to restore them. The task is to find all dependencies that hold in a given unexplored table. Unfortunately, it is computationally intensive. The number of possible FDs grows exponentially with the number of columns, and a 20-column dataset may have up to 10 million FDs. Nevertheless, several dozen mining algorithms for database dependencies have been developed during the last 40 years. Each of them solves the discovery problem in their own unique way. As a result, it is of great interest to have a framework that would allow to use efficient implementations of FD mining algorithms and implement different algorithms in a sandbox environment to assess their performance. To the best of our knowledge, Metanome is currently the only data profiling tool that provides its user with a framework for developing and testing dependency mining algorithms. It supports various data types and DBMS connectors, and it has a front-end web service. It is also written in Java. This choice allows rapid algorithm development, grants cross-platform capabilities, and supplies the developer with a multitude of libraries. On the other hand, Java-oriented technologies introduce several drawbacks. First, the code tends to consume more CPU and memory resources due to the JVM overhead. Second, JIT compilation and garbage collection increase fluctuations in measurements, lowering performance predictability. Finally, Java does not fully allow low-level optimizations, such as vectorization via SIMD instructions. This motivation has led us to develop Desbordante, meaning unbounded limitless in Spanish, a console application written completely in C++. It currently provides basic functionality for finding all approximate and exact FDs in a CSV table. Based on the pseudocode from their papers and corresponding Metanome implementations, we have carefully rewritten two algorithms: Tain, a classic FD mining algorithm, and Pyro, a state-of-the-art algorithm for approximate FD discovery. The source code is available on GitHub. In the following slides, we are going to demonstrate the performance of our Pyro implementation. We consider only Pyro since its internal complexity can provide us with more useful insights than a simpler algorithm like Tain. For our experiments, we have selected a number of real-world datasets listed on the slide. In the table, we list their important properties: number of rows and columns, their size, the number of exact functional dependencies, and the percentage of null values. All the experiments were run on a desktop PC running an Ubuntu-based OS. We have ensured a clean environment, meaning freshly booted systems, no extra processes run, system updates turned off, and so on. This was done mostly to ensure the reproducibility of our results. We obtained the time measurements by performing 10 launches and building 95% confidence intervals. Our first group of experiments aims to show that the C++ implementation outperforms the Java one in terms of runtimes and memory consumption metrics. We have evaluated and compared out-of-the-box performance of Metronome and Desbordante. The runtime results are shown on the plot. Note the logarithmic y-axis. It can be seen that Desbordante is clearly superior to Metronome on all but two datasets. The obtained improvement on the other datasets ranges from 1.2 to 3.4 times, being 2.1 on average. Desbordante is also superior to Metronome in terms of average memory consumption. The improvement ranges from 1.5 to 2.6 times, being 1.9 on average. The peak consumption ratios are usually even higher. Research question number 2 is dedicated to checking whether the performance of Metronome can be improved using simple techniques that do not require code modification. We have tested several runtime options that could affect Metronome performance. 3 versions of JDK, compilation settings, including the ahead-of-time approach, various garbage collectors, and initial heap size. These experiments have shown occasional little speedup on several datasets, but they haven't revealed a set of options that would yield at least a 10% stable speedup. The table shows the common results of comparing two options. One can't choose the best option based on these measurements. Finally, we have concluded that using the JDK 11 with default settings would be an appropriate choice. In research question 3, we have attempted to explain why exactly Desbordante is faster than Metronome. We have used perf, which is a tool for monitoring hardware and software events in Linux-based systems, to measure the number of various events. After the analysis, we have selected 3 factors as the most performance affecting: number of instructions, number of cache misses, and number of branch misses. Other events, such as TLB misses and page faults, are less crucial to performance. We have also noticed that CPU migration and context switch count of Metronome greatly exceeds that of Desbordante. This could be explained by the fact that Metronome, being a Java application, is a multi-threaded program. Therefore, it is prone to CPU migrations. Finally, our guess was the impact of the C++ code optimizer, as it may invest more time in resource-consuming optimizations than a JIT compiler. To check this, we have rerun our experiments with all 4 available compilation options that control code optimizer aggressiveness. However, the O1 optimization level, which enables only basic optimizations, already supplies sufficient performance, while increasing the level further does not reduce runtime drastically. During the early stages of this project, we have noticed that the confidence intervals were in some cases abnormally large. An extensive study has revealed 3 factors. First of all, Pyro is sensitive to random number generation. Therefore, we had to ensure that random number sequences are the same in both implementations. The next issue is that such variability happens on relations with a large number of nulls, such as CI public highway. See Table 4 for an example of such variability. Finally, modern CPUs adjust their frequency depending on the load. Therefore, we had to lock the CPU frequency. These were the actions that we performed to obtain the graph of the research question 1. Our final research question addresses decreasing the problem complexity. It is possible to set the maximum size of the left-hand side of dependency. In this case, the algorithm should terminate search space traversal early, thus saving time and memory. However, our experiments have shown that the algorithm behavior is more complex. Setting LHS to 1 or 2 attributes at max leads to a noticeable speedup only on 3 datasets: adult, Iowa, and CI public highway. Furthermore, it is possible that bounding the size of LHS would even increase computational complexity. Such cases are marked in bold in the table. In this paper, we have presented Desbordante, the first tool intended specifically for high-performance dependency discovery. The experiments have shown that Desbordante runs approximately twice as fast and consumes only half of the memory required by Metronome. It also highly reduces hardware event counts. Desbordante is written completely in C++, extensible and fully open source. As for our future work, we are planning to explore its tuning potential. We have not yet employed custom memory managers, custom data structures and libraries, SIMD-enabled algorithms, and multithreading. Furthermore, we are currently adding several other algorithms to our platform. Thank you for your attention.